BGP architectures and best practices. One of the speakers is Eli Dart. Eli is a network engineer in the ESnet Science Engagement Group, which seeks to use advanced networking to improve scientific productivity and science outcomes for the DOE science facilities, users, and collaborators. Eli is the primary advocate for the Science DMC design pattern and work with facilities, labs, universities, science collaborators, and science programs to deploy data-intensive science infrastructures based on the Science DMC model. Eli is also a key contributor to the ESnet network requirements programs, which collect, synthesize, and aggregate the networking needs of the science programs ESnet serves. Eli has over 20 years of experience in network architecture, design, engineering, performance, and security. The second speaker is Hans Addleman. Hans joined the International Networks team at Indiana University in 2015 and is currently the network architect for the group. He's also part of the Engagement and Performance Operations Center, where he leads the roadside assistant team, technical workshops, trainings, and participates in science deep dive workshops. So welcome, Hans and Eli. So I will turn to you. You have the control right now.
Wonderful. Thank you so much, Jorge. Eli, let me go ahead and share real quick, and just let me know when you need the next slide.
Okay. Thanks, Jorge. Thanks, Hans. My name is Eli Dart. I work for ESnet at Berkeley National Laboratory. And with my partner in crime, Hans, we're going to talk through so this is not a talk about the specific commands you might type to configure BGP. This is about the emergent behavior, right? What actually happens to your network when you use the tools that you're going to learn about later today in some of the more hands-on parts of this. So this is, if you want to think about it in terms of like a strategy talk or sort of really the behavior that we all want to bring about to make our science collaboration successful. And it turns out routing and in particular BGP are an important part of that. So go ahead, advance the slide, Hans. So we're going to go through a couple of things. I'm going to talk about routing architecture, sort of pan out, right, and look at the networking community in general, right, why this stuff's important, what some of the behaviors are, what some of the larger structures are that we see. And then Hans is going to get into some more details about how, so okay, we look at these larger structures, right, what parts of the BGP policy language or things like that, right? When you go and change things, how does it affect those aspects of the R&E routing ecosystem that we all live in? And hopefully the combination of these two things will then set the stage for the hands-on work. So next slide, please. So this is part of this NSF funded center called EPOC. It's a joint project between ESnet and Indiana University. Dr. Jennifer Schopf at IU is the PI on this, and then there are two co-PIs. One is Jason Zarowski in the Science Engagement Group at ESnet as well, and then one is Dave Gent at the IU Global NOC. And the idea is to partner with a whole bunch of different cyber infrastructure communities and the scientific community, right, across the NSF and DOE space to make science outcomes better using cyber infrastructure focused on 5 key focus areas, right? One is roadside assistance, which where Hans is centered. One is application deep dive. So this is understanding what a science collaboration or science project or scientific facility does with their data and does with the network, and how can we make those things better. Network data analysis. So for NetSage, figuring out who's doing what on the network, what it means performance-wise, and therefore, how can we inform our performance engineering work. Things like Science DMZ in a box, quote, quote, Persona in a box, right? Services for scientists and institutions, and then training events modeled on the OIN workshops and other similar efforts like this one. So let's pan way out and let's look at what networking sort of actually, what is this networking thing, this internet thing that we all sort of look at. Now, this slide is ridiculously simplified and ridiculously cartoonish, right? This is not intended to be a diagram of the internet. It's even a poor representation of a diagram of the internet. If you want a diagram of the internet, okay, go look up some of the visualizations that CADA does. They have some amazing stuff. You can like spend hours messing around in some of the pictures that they produce. It's pretty spectacular. This cartoon is intended to show a couple of things. One is that there are a bunch of different actors across the world, really, but throughout different sectors of human endeavor that all build networks for their own selfish reasons, right? And it turns out that when you build a network, it increases in value if you connect it to other networks, again, in the service of your own selfish reasons. So if you think about a network like Amazon, right? So Amazon builds a network infrastructure for their stuff, right? They have a logistics operation to run and so forth, but they also have an e-commerce operation to run, right? And their network is not of any value to them unless it's connected to other networks, right? Which have, as we say, eyeballs, right? So they connect to all the ISPs that provide residential broadband service so people can fire up their web browser and buy stuff from Amazon. Google has similar things, right? They build a whole bunch of networks for slinging their data around, for running their compute cloud, for providing services like Gmail or Google Search, YouTube, right? Things like that. And those services that they provide are only valuable if they connect them to other networks. But each of those interconnections only occurs for reasons that are of value, right? That increase the value for the entity that is building that network. So now if you look at the blue shaded clouds there inside the red circle, right? This is the science complex, right? This is what we call the R&E networking community. And this is another set of networks built by research organizations for the selfish reasons of those research organizations, right? There's a reason ESnet exists, right? ESnet is a mission facility built by the Department of Energy Office of Science to further the Department of Energy's science mission. That's why we exist, right? The state networks are designed and built to interconnect the state's universities, in many cases K-12, libraries, all kinds of other things, right? But they're built for those reasons. Internet 2 is built to provide services between and among the university networks and interconnect them to other networks like ESnet and other similar networks across the world. So, but these networks are all connected directly to each other, or connected to each other by means of exchange points directly, right? And the mechanism for exchanging reachability information is what we're talking about today, right? Which is BGP. But these networks, right, these blue shaded networks are designed and built to support science services and science applications. They're designed and built differently than the commodity networks of the world. Now, they all run the IP stack, right, and that's fine. But if you look at the way these networks behave, it turns out to actually be different. And it's because of how they're built and why they're built. So next slide, please. So the R&E networks are, as I said, designed, built, engineered for science applications, right? And so and the commodity networks are not. And we'll see more of that in a moment. But so what does that mean, right? What that means is if we want our scientific applications to perform well and behave well, we want to keep that traffic on the R&E network infrastructure if we possibly can, because that's the set of networks that are designed and built for the purpose. So what we want is to figure out a way that we can configure our networks such that traffic between University A and Lab Z, right, traverses science networks, D, E, and F, rather than going across commodity. And because each network is under its own administrative control, right, and in fact, each router in that network is making packet forwarding decisions locally, right? So, packet comes in, I look at the destination address, I throw that against a lookup table in my memory, right? I get an egress interface back, I forward the packet, right? That's a very local decision. And all those local decisions are made due to the aggregate behavior of a set of routing policies, right, that are distributed using routing protocols, right? And that emergent behavior then is what gives us this thing where we say we want all of the science applications to stay on science networks. So next slide. So let's look at why this matters. So here's an example from some troubleshooting work that we did a couple years ago. So somebody, was banging their head on a performance problem, right? We've all seen this. And they were trying to move some data between the Ohio Supercomputer Center and NERSC. And it's like, okay, well, this is slow. Let's figure this out. Do some trace routes. Okay, you're going over commodity instead of R&E. And so what do you do, right? Well, you characterize it, right, with persona, right? Okay, yes, performance is slow, and we were seeing sort of some strange behavior. Well, so Jason goes and fires up TCP dump and gets a packet capture of one of the tests. Okay, and so the interesting thing about this, right, is we were invoking their DOS machine, and I'll show you what that looks like in a second. But the key point here is this is a difference between what happens on a commodity network and what happens on a science network. So what does a multi-gig traffic spike mean on a commodity network? It means that somebody's launching a denial of service attack, and for the health of our infrastructure and for all the users that are paying us, to use this thing, we need to shut that down like right now. In the R&E world, that's like core mission. Right? That's a couple of DTNs slinging a couple of terabytes of data around, and a scientist is just trying to get their work done so they can save us from COVID-19 or whatever, right? So what does that actually look like on the wire, right? It looks like this. So you see the flow ramp up there on the far left side, right? So this is the y-axis is TCP sequence number space, and the x-axis is time, right? And so, we're moving a lot of data for the first second or two, and then it just gets killed. And that's it. Right? It dribbles through these tiny amounts of packets. It looks like most of them appear out of order from the perspective of TCP trace, and eventually the flow dies. Right? So this is what happens what was happening when a normal course of business data transfer between two computing facilities traversed the wrong network. So next slide. And this isn't the only example. So these are a couple of things that have been presented at TNC. So the first one there was a characterization of, again, commodity versus R&E. And not only did they see the same thing that we saw here in the US when the denial of service mitigation machinery was getting invoked, but they also saw packet loss on the commodity path. And if from looking at TCP loss plots and whatever, right, packet loss is not the friend of TCP performance, right? And so what this really means is if we allow this problem to persist, you end up with this thing where I have to debug it before I use it, right? And most scientists don't have the time or the expertise or the inclination to do that, right? It has to work when they walk up to the tool and use the tool, or they're going to figure out another way to organize their life. The second example was a multi-nation test of R&E versus commodity. And one of the things that they brought up, and this is something that a bunch of us have been saying for years now, hop count is not a good measure of performance, right? They're like, yes, in this case, the R&E paths perform better even with more hops. Well, yeah, Of course, modern routers are ASIC based, right? The days of CPU based forwarding are long gone. And so what we want is the path that's engineered cleanly and that has the available bandwidth and has the right behavior. Doesn't matter if it's got more hops. I'll talk more about that in a minute. So there's this common theme here, right? Which is that R&E networks are engineered to support scientific applications. Commodity networks are not engineered to support scientific applications, right? They're meant to support a bazillion smartphones and Gmail and Office 365 and all the things, right? Which is fine. We need those networks. We just don't want to be running high performance data transfers between DTN clusters over those networks, right? So let's move on to the next one here. So what is it? That's the background, right? So what do we do, right? So we want to keep R&E traffic on R&E networks. The mechanism for doing that is BGP policy, right? So if you think about this from a theoretical perspective, routing announcements attract traffic. If I announce you a prefix, I expect to see traffic toward that prefix coming from you. And so in aggregate, routing determines, right, the path that a packet takes or that traffic takes through the network. And we have a set of policy tools to do that. Now, what does BGP actually do, right? BGP is a path vector protocol. And the path is composed of autonomous systems, right, which are administrative domains if the route has passed through. And so in its default behavior, BGP prefers the shorter AS path length. And so that's fine. And if we have path lengths that are the same for a given prefix, then we go down a whole decision tree. It's called the BGP path selection algorithm. I'm sure you're going to learn about that if you haven't already. Here's the thing. Remember, we just talked about two things. Science networks are engineered for science applications, and hop count is not a relevant performance metric. So in general, the AS path on an R&E route is going to be longer than the path on a commodity route. And the reason for that is, let's go to the next slide, I think has the graphic here. Yeah, so let's say we have two campuses. They both peer with the same commodity provider, Verizon or somebody, right? And they also have a connection to the regional. And those regionals both have connections to internet too. Well, okay, so the path through R&E is 100 gig clean, but it's got a longer AS path. And it's engineered to support scientific applications. The path through the commodity provider, it's got a 10 gig. And by the way, it's got all the YouTube and software updates and O365 and all the other Netflix, all the other goop on it already. So it's not even a clean 10 gig, right? There's a bunch of background traffic on it. So which would you rather send your science flow across? Well, if all you do is take your BGP feed from your regional and from your commodity provider and throw them all in the same bucket, right? You're going to hear so campus 1 is going to hear the routes from campus 2 from its regional and from the commodity provider. The commodity provider is going to have the shorter AS path length, and so it's going to take the commodity provider. We've seen this in production multiple times. This is not a theoretical problem. Next slide. So from a backbone perspective, right? So there's a set of tools that you have to manage this sort of stuff, right? And ESnet gets pretty complicated and pretty involved in this. And so we use BGP communities, which you're going to hear about. So we tag routes when we bring them in based on attributes of the peering session that we use to get the route. And we have a set of local prefs that we use, that we assign based on those communities. And that allows us to separate traffic by the type of network that it's going to, or separate routes and therefore traffic, right, by the type of network that we're talking to. Because in the R&E world, AS path length and hop count are not relevant performance metrics, right? Now, this is not necessarily something that we're saying you should do on your campus, but this is how a national backbone can use BGP's policy tool set to actually put together very complex behavior, right, that allows scientific applications to do the right thing under a variety of circumstances. So next slide, please. So this is not to say you should set up your campus perimeter like the ESnet core, right? That's not the point of this at all, right? The point is there's a set of policy knobs in BGP that allow you to differentiate between different kinds of routes as long as you tag those routes with the right metadata. And if you do that in a sane way, then you get stable emergent behavior, right, that allows scientific applications to see the high performance that we've all engineered our science networks for. So, you know, and those same policy knobs mean sometimes different things in different contexts. So in a backbone context, right, we have a bunch of different things to worry about, right? Different peering sessions, sometimes on different coasts or, you know, separated by thousands of miles. We need our stuff to be resilient to route leaks. So somebody makes a mistake, we don't want that to affect our network. Yes, we implement BCP 38. Absolutely we do. And you should too. Even campuses should. If you don't know what it is, look it up, do it. On campus, though, there's some other things to do as well, right? So your routing policy might be a key element to supporting your security policy, right? And that's great. Common to both of us is this goal of high performance for scientific applications. And at the end of the day, right, you know what you need to do with your network on your campus, right? And it doesn't matter what I say or what anybody that's not you says, right? You have to know your own network and do what's right for your network to make sure that your users see the benefits from the network you've built for the reasons, right, that you've built it, right? Because again, networking is inherently both a community effort and a selfish effort, right? Everybody's got their own mission, and we need to integrate with each other well to also accomplish our collective mission. So understand the tool set that you got, and everybody has to make the local decisions that allow science traffic to stay on science networks so that we as a community end up with this emergent behavior, right? Which is that scientific applications that transfer data across administrative domains see high performance in the general case. Next slide. Okay, so that's it for me. Let's hold questions for now. I'm gonna hand this over to Hans, and then we'll take questions at the end. Thanks.
Thanks, Eli. So in the roadside assistance in EPOC, we over the last couple of years have been working with people doing all sorts of different performance engagement type things. And two examples really stuck out to me as Eli and I were putting this deck together. These are real world and happened, in about the last year. This one, the campus had two peerings to a regional provider and also a commodity peering. It turned out that they had brought up their new 100 gig to their regional provider, but still had a 10 gig laying around to that regional while they were, transitioning, and they left it there for backup. Turned out that BGP hadn't been modified properly or, optimized, let's say, for the 100 gig fully, so that they saw a number of different campuses and other DTNs sending data through that 10 gig, which unfortunately was congested at the time. And a little bit of working with them, we saw, as you can see, their throughput for that specific file transfer jumped tremendously with a few tweaks to their BGP. And then, click there. Another example. This one is exactly kind of what Eli was talking about with OSC, except in a different case. You can actually see there that their routing table, sometimes we get to see routing tables, sometimes we don't. They actually were preferring, with their local pref, hammer, if you will, to use the commodity path. Worked with them to fix that, explained how local pref works, went back and forth. It was actually kind of interesting. In that case, their regional provided commodity, a link to Internet 2, a link to ESnet, and a number of different routes to different things. And they provided it as one big connection. one big BGP blob of routing data. So in that case, it was actually up to the campus to sort out and figure out what their best move was. And to figure those kind of things out and set those knobs, we can do some BGP care and feeding. So, as we've talked about, BGP, much like TCP, it just works, right? But it may not be the most performance you can get out of it, right? Eli and I have talked for the last 26 minutes about the need for tuning this and actually taking a look at your BGP policy and working on it. And it just needs some care and feeding. And unfortunately, the little diagram seems to be missing in the slide, but the BGP path selection, depending on what vendor you have, could be a 10 to 13 step process. Luckily, we normally don't have to care about much of that 10-step process and can worry about using local pref mostly to our best advantage. I'll talk about communities here in a minute. If you really need to, you can do AS padding or even look at meds. But really here, the key is, and actually Michael Lambert told me this last week when we were giving a talk like this, he said, everything but local pref can be overwritten by your peers. So really local pref is what you want to use to steer your traffic and steer your routes best. So talking about local pref, it is a per prefix, per route kind of thing. You actually need to set it on each route that you care about modifying. It modifies outbound and the higher is preferred. Hopefully later in the hands-on tutorials, you'll see kind of some of this. BGP Community Strings, I actually probably should have talked about this first in the slide deck. They're very, very useful. They are something you have to set, and then also, you can use it internally. But if you do attach a prefix to attach a BGP string to a prefix and advertise it to a peer, you should have some kind of public website that says what that means, right? Unfortunately, it's usually just your AS number, colon, and then some random number that you've determined. That number can mean any different things on many different networks, and so you should publicize that or at least talk to your peers about what that is going to be. Common uses would allow you to change local pref, DDoS mitigation, things like that. And as you're talking to your regional or national network, you're setting up BGP with them, talk to them about what they have. Ask if they have any published BGP community strings that could help you better understand your traffic and steer your traffic. Looking quickly here at Internet 2's public BGP strings, you can see there's quite a number of different things that they offer. And actually, this is just some of the ones that I thought were more interesting. There's a much longer list. As you can see, as we've talked about, they allow you to change your local pref. They default everything to a local pref of 100. But if you send them that prefix or that community string on your prefix, they will change your local pref facing back towards you. They identify where the prefixes come from, whether it be Amazon or another cloud provider, or even where they get that prefix across the country or internationally. So you could see a prefix that says New York or Los Angeles, and depending on where you are in the country, you could change where you're accepting or where you're preferring that prefix. They even allow you to discard all traffic destined to a prefix that you advertise to them, in case you're getting DDoS or something bad is happening. And then you can, as a last resort, tell them, hey, why don't you just prepend or add a AS path to this route, and then here's what AS path padding does, as it kind of sounds like. You can add ASs to your prefix to make it look less good to your neighbors. Now, I would caution, I have seen in internet routing tables, and if you go through, you'll see this, like in route views or something. Some people will pad 5, 6, 7, 8, 9, 10 times. At some point, it gets, I would say, a little ridiculous. Usually, just padding once or twice can really affect where that traffic is being accepted and directed. And then, as a last thing to use, if your communities, if your local pref isn't working, your upstream provider may actually attach a multi-exit discriminator to a prefix they advertise to you, and basically try to attract your traffic. That's pretty far down in the selection process, and like Eli said, local pref is probably your best tool. And like Michael said last week, it's the only tool we have that our peers won't overwrite on us. So that's about it. I kind of blazed through that. I think we do have some time for questions now. And let me see if I can pull up the Q&A and chat here. I'll stop sharing just so I can actually see that. I think Eli is still around.
Yep, still here.
Great.
Yeah, so feel free to ask questions or dump stuff in chat. Okay. Given the difference in traffic patterns between enterprise and research, how do you secure yourself on an R&E network at the network level, or do you inherently trust that traffic? This is something that, there's another line here that says, maybe it's outside the scope of a BGP presentation. There's a couple of things, right? So routing is going to tell us where traffic's going to go, and whether you can reach a given prefix, right? So if the prefix isn't in your table, right, the route is going to drop the traffic, right? So that's fine. But routing and filtering aren't the same thing, and packet filtering and application analysis and sort of host state inference aren't the same thing either. And so in a lot of cases when people talk about routing security, right, they're talking about things like validating the origin of prefixes, right, and things like that. They're not necessarily talking about deciding which hosts can exchange traffic, right, in a layer 3 filtering sense, or what applications can exchange traffic in a layer 4 filtering sense, right? Or let alone anything like web application firewalls. We're going to let these regexes through, these kinds of things. I think nobody should be inherently trusting anything, right? All traffic should be subject to policy. And so the question then is, how do you implement that policy, right? And there's a whole other set of discussions around how to enforce the security policy you have in a performant way, and that gets us into the science DMZ model, which we're not really talking about here. So I guess I would defer most. Hans, do you have anything to add to that?
No, I think, yeah. Never trust anyone, right?
Yeah.
Unless you know them really well.
Well, and even then, right? I mean, all traffic is subject to policy, right? It just has to be these days. And so, the question then is, how are you going to implement the policy that you have?
Jeff Bryant asked the next question: does metadata reduce the size of the data packets, or is it consumed elsewhere? Jeff, so the metadata like BGP communities and things like that, and local pref and all that, if that's what you're talking about, that kind of data is only shared in the BGP updates between routers. Once a BGP is converged and established between two routers, none of the packets that flow between those routers have any of that BGP metadata on them, right? So a user's packet from campus A to campus Z will have very little of that kind of thing that we're talking about for BGP to understand where to direct your traffic.
Yeah. So, I mean, to expand on that a little bit, right? BGP is itself a network application, and there's a process running on each router that runs the BGP protocol and has a bunch of memory that it uses for routing tables. TCP port 179 is used for that, and all of the routing tables, prefixes with communities on them, all that sort of stuff is all data from the perspective of that BGP application. That data is exchanged between BGP applications using TCP over port 179. And so that, that's this interesting thing, right? Where the routing information and the packets actually being forwarded based on that information are ships in the night, right? They're completely, they're totally different things, right? And what you want is for the routing protocol to distribute all this reachability information so that the local forwarding decisions made by individual routers when they forward individual packets are sort of coherent and sane from an aggregate perspective, right? And so that's why things like protocol convergence time and so forth are really important, because if the router, if the table hasn't converged, as Hans was talking about, right? If your table hasn't converged yet, my router, I haven't converged yet. Hans is converged, right? He's stable, he's happy, right? He's just doing updates, right? And I'm getting like a full table from him. Until I get all that, I'm not going to be able to make decisions that are congruent with the rest of the world. And so I may hand Hans a packet for which I'm actually the best exit once all the routing protocols are converged. And so Hans will just hand it back to me, right? And so you can see this packet ping pong back and forth across a link between us until TTL expires and the packet dies, right? I mean, this is one of the things that it's called black holing traffic, right? Because from the application's perspective, the packet just got dropped, right? So the routing table exchange, right? BGP itself is a network application that's separate from all the traffic.
And it with full tables, back in the day, a full routing table convergence could take 5 to 10 minutes. Nowadays, across a performant regional network, campus network, things like that, that full convergence only takes 30, 45 seconds usually. So you don't black hole for very long, right?
Yeah, unless you got an old box.
Yeah, well, yeah, if you're running something super old, yeah.
Other questions?
And I'll be hanging around in chat room. I don't know what Eli's schedule looks like. So if you do have questions, just hit me up there, or, if you have questions about BGP or anything like that for your campus network, do feel free to reach out to EPOC, epic@iu.edu. And I'm happy to take this to email.
So yeah, Hans, Eli, I have a question. How do you see BGP evolving in SDN networks?
Boy. Well, so I think from my perspective, at least, there's a couple of different things happening here, right? One is that the internet as a whole uses BGP for layer 3 reachability. And so if you're going to integrate with the rest of the internet, somehow you're going to need to speak BGP, right? Because that's the way that's the way your prefixes get injected into the rest of the internet so that people can find you, and that's how you get to see what the rest of the internet is, right? So that's how you can find hosts on the rest of the internet. Now, what an SDN network does with that routing information, right, and how that influences packet forwarding, right? That's up to how you program the network. And I think it's pretty clear that some of the tooling that SDN gives us allows us to more flexibly program the network based on whatever information we have. For the foreseeable future, I think that integrating with the rest of the internet is going to require somebody to speak BGP, both to advertise the prefixes you have and to learn about the prefixes somebody else has. So that's my perspective anyway.
Yeah, that's a good answer. I think BGP, yeah, Eli, you're right. BGP is going to be around for a while. I mean, there's a lot of really interesting use cases for SDN, but not in BGP space yet. done in the worldwide layer 3 kind of space.
Other questions? Okay.
Well, Hans, Eli, thank you very much for the presentation. I just want to tell everybody that the slides will be online at the end of the day, and the slide of yesterday and the recording of yesterday are also online right now in the